Hello everyone, I'm J Wildberger. Today we're going to be looking at complex polynomials and their factors. And we're going to prove an important couple of theorems called the factor theorem and the remainder theorem. And we're going to talk a little bit about another result, very famous, called the fundamental theorem of algebra, which is maybe not entirely a theorem. So we're talking about polynomials with complex number coefficients. For example, something like maybe z cubed plus I times z squared minus 2 plus 3i times z plus 5 minus 4i. Okay, so this is a polynomial in z. So z is, generally speaking, a variable taking on values in our complex number system. Okay, so we say in general, complex polynomial is an expression of the form, say f equals, say a0 plus a1z plus a2z squared up to, say, a sub n z to the n, where each of the ai's are themselves complex numbers. Okay, so I prefer to think of a complex polynomial as being an expression, but associated to it is then a function. We can associate to this the function f of z, whose value at z is the same expression. So it's almost the same thing, just a slight change in meaning. The reason why it's sometimes better to think about an expression is because actually there's a lot of different functions that can be associated to the same polynomial. For example, the same polynomial could be interpreted as a function from the interval 0, 1 to complex numbers, or it could be interpreted as a function from, say, natural numbers to complex numbers, and so on. Okay, so this function takes values from complex numbers to complex numbers. Okay, and what about the degree? So if the top coefficient, a sub n, is not equal to 0, then we say that the degree of f is n, i.e. we might write degree of f equals n. And the special polynomial f equals just 0 does not have a degree, okay? Is just sometimes written 0, and its degree is not defined. Okay, so we can do arithmetic with complex polynomials just like we can for regular polynomials. So I'll just give you some examples of this arithmetic. It's pretty straightforward, just some simple examples. Let's start with the highest power of z starting. So let's maybe say z squared plus 2z plus I. Okay, there's one polynomial. And here's another one, say z cubed minus 1 plus I times z plus 3. Okay, well, the sum is going to be z cubed plus z squared. And how many z's are there? 2 minus 1, so that's plus 1 minus I times z. and the constant term will be 3 plus I. Okay, and similarly we can subtract, and multiplication is as you would expect. So maybe we have z squared plus z minus 2i times, z plus, to make something not too complicated, z plus I, that's going to be. So we'll expand everything out. Z cubed, multiply everything by z cubed plus z squared minus 2iz, and then we multiply by iz squared plus iz plus 2, because I squared is equal to minus 1. And that simplifies perhaps to z cubed plus 1 plus I z squared. And how many z's? Maybe minus iz plus 2, something like that. Okay, if a polynomial, say f of z, is a product of two other polynomials, say if f of z equals p of z, q of z, then we say then p and q are factors of f. And then factoring polynomials is an important issue, a lot like factoring numbers, but the factoring story in polynomial land is much richer than it is for numbers. And it's especially here with this question of how polynomials factor that the complex number framework is particularly important and instructive. Okay, so let's have some practice factoring some things. And we'll start with some relatively simple ones. Maybe z minus a. Okay, so here I'm going to, well, that's just factors as z minus a. A here is going to be some complex number c, which we're going to regard as fixed. Okay, and z is our usual variable. So what about z squared minus a squared? That factors as z minus a times z plus a, because it's a difference of squares. What about z cubed minus a cubed? Well, we did talk about this kind of thing in the special case when a was 1. Now it's a little bit more general. So this thing still has a factor of z minus a. And then what's the remaining factor? How do we write that down? Well, the highest power should be z squared, so that z times z squared gives us this z cubed over here. But then there's a minus a times z appearing here, so we should compensate for that by putting plus a times z over here, so that this product here, this z times a z, will cancel with that other one, leaving 0 z squareds. And then we have how many, what's the constant term should be? Well, it should be, a squared, because then the a squared times minus a gives us the minus a cubed, and also together the constant term will then be a squared times z from here and minus a squared times z from that. So that's a complete factorization. So once we've done that, the more general story is almost clear. Let's do one more. Z to the fourth minus a to the fourth will be z minus a times z cubed plus a times z squared plus a squared times z plus a cubed. Okay, so hopefully now the pattern is clear, and we can write down, so similarly, z to the n minus a to the n always has z minus a as a factor. Okay, so that's important because of the following application of these identities. So suppose that we're interested in, say, for example, z squared plus iz, I'll make it a complex thing, plus 2. Okay, so suppose I take this polynomial and I subtract a corresponding number, which is this thing evaluated at a. So replace the z's with a. Say a squared plus ia plus 2. I'm going to want to look at this combination because it's quite interesting. So what we can do is we can write this as a number of sums of this kind. So we can write it as, first of all, z squared minus a squared. And then there'll be something involving z minus a. So it'll be plus I times z minus a. And then, well, plus 2 minus 2. Okay, 2 minus 2. And we note that that's equal to z minus a times z plus a from the first factor plus I from the second factor. So altogether we get z minus a times z plus a plus I. So what this shows actually is a special case of the following factor theorem. A factor theorem for complex polynomials, which is that if f is a complex polynomial and a is a fixed complex number, then f of a equals 0. So in other words, a is a 0 or a root of f precisely when z minus a is a factor of f. So this is a characterization of when we have a linear factor z minus a. So this linear factor z minus a is a factor of f precisely when f of a equals 0. All right, so let's give a little proof of this. So there's a two-way implication here, so it has to be proven in two different ways. So if z minus a is a factor of f, then we can write, say, f of z equals z minus a times some other polynomial, say p of z, for some polynomial p. But then when we plug in a, we get f of a equals a minus a times p of z, which is indeed 0. So that proves this implication. If you allow me to go up here, it proves that if z minus a is a factor, then f of a equals 0. Now in the other direction, if f of a equals 0, what we can do is we can apply this kind of expression that I've given a special case for here. So what we're going to do is we're going to consider then f of z minus f of a. We know that that expression, okay, is going to be equal to z minus a times some polynomial, say q of z, for some polynomial q of z. Again, the reason for that is exactly as I've indicated in this example here. It's simply an application of these kinds of fundamental equalities to realize that every term is divisible by z minus a. So let me explain that a little bit in more detail. So I'll say because if f of z, say, is equal to, I'll use some other number, say c0 plus c1 z all the way up to, say, cn z to the n, then f of z minus f of a will be c0 minus c0 plus c1 times z minus a plus c2 times z squared minus a squared plus all the way up to cn times z to the n minus a to the n. Okay, so we're taking just the difference of f of z, and the same thing when you plug a in. So we're going to get all these terms here. This is going to be 0. And all these terms here are all divisible by z minus a, exactly because of these identities that we've already established. Okay. So this is divisible by z minus a. This is divisible by z minus a. All of them are divisible by z minus a, even up to there. So this is divisible by z minus a. So that establishes this claim that that we have. And now, if we haven't used the fact that f of a equals 0, so now, since we're assuming that f of a equals 0, this becomes f of z minus 0. In other words, f of z equals z minus a times q of z. Okay, it's exactly because the condition that f of a is 0 means that this thing is going to be 0. And that allows us to conclude that, therefore, z minus a is a factor of f of z. Okay, and this kind of understanding goes back to Descartes back in the 17th century. Okay, so you'll probably have seen this for, say, real polynomials, hopefully, but the argument is quite general. So if f is a complex polynomial and a is in C, then these two statements are equivalent. That, get rid of this thing, that f of a is equal to 0 precisely when z minus a is a factor of f. There's another consequence of what we've just done, sometimes called the remainder theorem. Let's write that down too. So the remainder theorem takes this equation that we've just established and we apply something else. So it states that if f of z is divided by, say, z minus a, where a is a complex number, then the remainder is f of a. Let's have a look at proof of that. Okay, so we know from above that f of z minus f of a equals z minus a times some polynomial q of z, for some polynomial q of z. But we just rewrite this as f of z equals z minus a times q of z plus f of a. Okay, so what's that telling us? That's telling us that if we divide f of z, if we divide this thing by z minus a, then the remainder that we get after we've done that division is this number. Okay, so this is a linear factor. When we divide by it, we're going to get something of lower degree, that's a constant, and that constant is f of a. Okay, so that's great. And now I have to say something about the most important sort of result or understanding in this context, which really makes the whole complex polynomial story so important, and that's the fundamental theorem. Fundamental theorem of algebra. And I'm forced by intellectual integrity to put quotes over this theorem because, as far as I'm concerned, this is only partially a theorem. It's actually more an approximate result rather than an exact one at this current stage in year 2020. Okay, what is the theorem? The theorem is that if f, or f of z, is a complex polynomial of degree greater than 0, that is, it's a linear or quadratic, it's not a constant. Okay, so i.e. f of z is not a constant polynomial, it's not constant. Then there is a complex number, say a in C, such that f of a equals 0. So every non-constant complex polynomial has a 0. So I have to qualify this. I'm sorry, but I have to do it. Qualification. Okay. This is only approximately true. And in fact, to be honest with you, there have been many theorems of this result going back to Euler. Well, Euler struggled with it. Gauss gave some proofs. Other people gave proofs. Gauss came back to this theorem many times in his career. I think he realized that his proof was not really ironclad. He was always looking for a better way. And since then, many people have given proofs. And from my point of view, none of them are entirely satisfactory. The reason is because, well, first of all, two reasons, I suppose. That, first of all, the underlying number theoretic framework is that of these complex numbers involving infinite series or infinite decimal expansions, and that's, I think, problematic. And secondly, because the proofs aren't really algebraic. And it's supposed to be a theorem of algebra, but when you look carefully, none of the proofs are entirely algebraic. Euler tried to find an algebraic proof, but he couldn't. And so I think this is still a big to-do in modern mathematics. And if you manage to find a purely algebraic proof of this, you will be ultimately very famous. Okay, so to illustrate these things, let's have a look at this little program. It's called Scientific Workplace. It allows me to do typesetting with LaTeX, but it also has a nice computational engine in it, so I can compute things. So here's a product of three linear factors, z minus 1, z minus 2, z minus 3. And I could get my machine to expand this out. We get the polynomial z cubed minus 6z squared plus 11z minus 6. Now, if we were in the ordinary high school domain, we probably wouldn't use z. We might use x instead. We might think about graphing this function. Let's see what happens if we do that. Say plot 2D rectangular. Okay, so maybe it's a little bit clearer if I make the y-axis a little bit less big, minus 5 to 5, let's say. Okay, so now it's quite clear that we have these 3 zeros at the points 1, 2, and 3. And that's no surprise because we started with the polynomial written in factored form. Now, suppose that I just go back to this thing here and ask my computer to factor this thing. So modern computers are very good with polynomial algebra. It can factor this very quickly. But suppose I change things a little bit. Suppose I say change it to z cubed minus 6z squared plus 11z minus 6, say 6.1. Okay, and ask it to factor that. Well, first of all, it converts things into decimal because I have a decimal in here. But you see, it hasn't actually factored things. It's left it as a cubic. Now, why do you think that is? It's because actually it's much harder for the computer to factor this. And in fact, it can't really exactly do this. Let me illustrate that by taking the corresponding equation over here. Let's first of all see what it looks like computationally. Plot this one. Okay, I should change the scale so it looks similar. Okay, so it's very similar, but you can kind of see that the zeros now are offset a little bit from what they were. Okay, this small modification to the 6.1 has changed the location of the zeros. So let's actually look at more care at this, where these zeros actually are. Let's take this expression, and I'm going to get my computer to actually solve this, set it equal to 0, and we'll solve it numerically. Okay, so what do we get? We get values 1.05435, x is 3.04668, or maybe it's 1.898. So something pretty close to 1, something pretty close to 2, something pretty close to 3. But note that these are not really the true zeros, okay? This is only what the computer gives me because I've asked for a resolution of 5 decimal places. So if I'd asked for 20 decimal places, well, there'd be longer expressions with more decimals. But even then, I would not have an exact solution. Okay, so an exact solution is not really obtainable. So there are various algorithms that the machine uses to find zeros, some of them going back to Newton. And these are typically algorithms that they keep on going. They get better and better and better, meaning that you're adding more and more decimals as the computer is allowed to churn away. But to actually get a complete algebraic zero, like we did in this original case, because we sort of cooked that up, that's actually not going to be possible unless you run these programs till the end of time. And at that point, then you have some infinite decimal that will work. But it's debatable whether there really is such an arithmetic involving infinite decimals where your computer has run to the end of time. So that's a problem. Now, in the cubic case, there are some classical formulas that go back to Cardano and others in the 16th century that allow alternate expressions for the solutions to a cubic equation like this in terms of square roots and cube roots. But for a general n-degree equation, there is no such corresponding sort of magic algebraic formula, and this is the sort of the standard default situation. So let's go back to our situation with this fundamental theorem of algebra. The theorem asserts that for any complex polynomial, even ones with complex coefficients, if it's not a constant function, then there is a zero somewhere in the complex plane. Now, what I've just been telling you is that this kind of statement ought to be interpreted in an applied or an approximate sense. That is, we can get at complex numbers in the complex number plane that are pretty close to being zeros, but actually the discrepancy between the f of a and the 0 is small, and we can get that smaller and smaller, but we can never, in general, get rid of it altogether. Okay, but nevertheless, this is still a completely remarkable fact. It's one of the truly remarkable fundamental aspects of mathematics. Okay, it has huge consequences, even if it's just an approximate statement, actually. Even so, it has a lot of very important consequences. And one consequence of that is what we might call the factorization theorem. Okay, and we'll state it in the usual way, but it again probably needs to be qualified to make it approximate. That if f of z is a complex polynomial of degree greater than or equal to 1, then it can be factored into a product of linear factors of the following kind, that we can write it f of z equals some constant c times some linear factor z minus, say, a sub 1, and then z minus a sub 2, all the way up to z minus a sub n, where these numbers c, a sub 1, a sub 2, all the way to a sub n, all are complex numbers. In fact, the a sub i's are just the zeros of f of z. So because of that factor theorem that we already talked about, whenever you have a 0, then you have a linear factor, and conversely. So finding linear factors like this is really just the same as finding zeros. So in other words, f of ai equals 0 for I equals 1 all the way up to n. Okay, so this is a very nice theoretical result, even if it's actually not exactly true, even if in practice with your computer you can really only do the kind of thing that I was showing you, that you can get decimal approximations to zeros, so in other words approximate zeros, and then you can use those to cook up sort of approximate linear factors. So the actual equality that's sitting here is maybe better, represented by an approximate equality. Okay, but nevertheless, traditionally this has been a very important kind of theoretical result, and we'll see in the next talk that there's further consequences of it. So see you then.